Google's chief scientist, the man who built MapReduce, the TPU, and the systems Gemini runs on, sat on stage at Y Combinator this week and named the assumption almost everyone in AI still gets wrong. You think an agent runs for an hour, maybe two. He is running them for days, sometimes weeks, on a single task. Then he handed the room his rule for what to build: target the problems where today's models succeed 1% of the time, not 20. And in the middle of the talk, he mentioned a free document that teaches any model to optimize code the way he does. We went looking. It's real, it's public, and it's linked below. 7 moments for builders, fact checked. But first, listen to him grade his own most famous prediction.
Yeah, I mean, I feel like the models have been getting a lot better at sort of agent-based, longer-running coding tasks, and it seems pretty clear that they are now actually pretty capable. And depending on exactly your definition of junior engineer, it seems pretty spot on, I would say.
That's Jeff Dean grading the prediction he made in May of 2025 that AI would reach junior engineer level in about a year. His verdict now: spot on. He joined Google in '99 when it was 20 people. He built the systems the modern internet runs on. He's on stage with YC partner Diana Hu, and the full 57-minute talk is linked below. Here's what most people will miss. Moment 1. Diana asks him, "What's one assumption 6,000 people in this room hold that is already false?" His answer is the ceiling on every agent you've ever launched.
Yeah, that's a good question. I mean, I think probably one thing is people don't quite realize how possible it is to have, agent-based systems that can run not just for an hour or 2 hours on a problem you care about, but for some problem domains and with highly capable models underlying them, you can get them to run for days or weeks and do really, really complicated tasks. And I think that's, some people are starting to see inklings of this, but I don't think everyone has really internalized this. And that's going to be really a pretty big deal.
What's a particular task that you have run that has run for weeks? What was it? What did you tell the agents to solve?
Yeah, I mean, I think you can tell agents to go off and implement, um, completely new versions of software in different programming languages that might be, have better safety properties or better performance properties. And then they can go off and actually do that in a, pretty serious way.
Days or weeks. And notice, he scopes it honestly. Some problem domains, highly capable models. But here's why this lands. 3 days earlier, on the same stage, the creator of Claude Code showed a prompt that had been running for 2 weeks. Bun's entire runtime got rewritten in 11 days. Google and Anthropic are now saying the same sentence independently. The ceiling on agent runtime is not the model anymore. It's whether you can check the work. Hold that thought for moment 5. Moment 2. It's 2013. Deep learning just made speech recognition actually work. And that success almost broke Google. Jeff Dean did the math on a napkin, and the napkin said, if this feature gets popular, you have to build a second Google. Listen to what they did instead.
Yeah, I mean, I sort of had done, we were starting to see really good quality results on the sort of deep learning based speech systems, speech models we were training. But they were computationally expensive compared to the old speech system, but they halved the error rate. So that was like the equivalent of 20 years of advances in speech recognition in just a few months of like fiddling with the model and scaling it up a bit and getting better data. And so we started to get worried that if speech worked a lot better, people would use it more. And so that back of the envelope calculation was really about that. Like, well, what if people start to use speech recognition more to dictate emails or to talk to their phone or whatever? And yeah, it turned out that we realized that we needed some better solution than running on CPUs at the time. And so we came up with TPUs, which are sort of very specialized for essentially low precision, dense linear algebra, which is at the heart of nearly all of the modern machine learning algorithms we use today. And if you build a specialized chip for low precision, dense linear algebra and can't do anything else, that turns out to be really useful for machine learning inference, even though it can't run Chrome or Word or whatever. And so that system produced a chip a couple years later that was 30 to 80 times more energy efficient than CPUs and GPUs of the day, and also much, much lower latency, like 20 to 30x lower latency.
We checked the numbers. Google's own history of the TPU tells the same 3 minutes a day story, and the 2017 paper confirms 30 to 80x efficiency. One napkin calculation became the hardware Gemini trains on a decade later. So Diana asks the obvious question: what's the napkin math everyone in this room should run tonight? His answer is a method, not a number.
Yeah, I mean, it's always hard to say. I think about what problems you see and whatever it is you're thinking about, what bottlenecks you see, and are there very different ways of thinking of the solutions to some of those problems that would get you, an order of magnitude or 2 orders of magnitude better performance or capability or whatever it is. Because sometimes if you just squint at a problem and you think about not necessarily being anchored on exactly how that problem is solved today, but how you would solve it from first principles, you can come up with really good ideas that are, maybe not what other people are thinking about.
Moment 3. Years ago, Jeff Dean wrote a list called Latency Numbers Every Engineer Should Know. It got taped to a generation of monitors. Dinah asks for the 2026 edition, and his answer collapses the whole list into one unit: energy.
Hmm. And one interesting thing that I've heard you talk about is that nowadays, the unit that you measure everything is energy.
Yeah.
You pointed out that doing a calculation or math costs about 1 picojoule, but moving the data and doing data I/O costs 1,000 times that.
Yeah, just bringing it in from HBM on an accelerator into the processor so it can actually compute on it. Yep.
1 picojoule to do the math, 1,000 to move the data to where the math happens. That single gap explains why batching exists. You amortize the movement across a batch, which is also why low latency is so hard. And it's why he says the next it fits in RAM moment is specialized inference hardware. Imagine his words, latency 50x better than today. If your product idea dies because tokens arrive too slowly, that's not a model problem. It's an energy problem and it's being fixed. Quick pause. If this is useful, follow us on Instagram and Facebook. Want to back what we build? Become a member on YouTube or a subscriber on Facebook. That's the ask. 4 moments left. The next one is a cheat code you can download. Moment 4. His next frontier is context engineering. And he's blunt that it's the layer anyone in the room can own because it needs an API key, not a GPU cluster. Then Dinah asks if he does this. And he casually describes a skill he and Sanjay Ghemawat, his coding partner of 25 years, wrote a few weeks ago.
Sparks. But then without an agent-based system, what you usually do is you measure what the current performance is on some benchmarks you care about. You make some modifications to improve the performance you hope. Then you rerun the benchmarks, see where things improved. You run maybe a broader set of benchmarks, measure the cache footprint of things. And so we wrote a skill that basically taught the model how to do most of those things in various sequences so that it could actually, do self-improving benchmark measurement, code changes, measure the performance improvement, and then iterate on that. And that seemed to work pretty well for some kinds of problems. And it really just is us giving the approach we would use as people to the model in a form that it could use.
Access to this.
We actually published a document maybe a few months ago called Performance Hints that Sanjay and I wrote. That's like a 30-page document about various kinds of performance tricks. And some people have taken that and then given it in summarized form to various models and seen that that model can now get better at reasoning about performance issues in code.
So you heard it all here. You could actually get your own, optimize your own code like Jeff Dean if you take this paper that you published from Performance Hints.
Yep.
It's all free available. So you should all try it.
We went and found that document. It's real. absale.io/fast/hints. Performance Hints by Jeff Dean and Sanjay Gemawat. Published this past December. Free. Direct link below and in the PDF. Read the workflow back. They didn't fine-tune anything. They wrote down how two of the best systems engineers alive approach a performance problem, handed it to the model as a skill, and the model started doing the loop. Benchmark, change, remeasure. Your 20 years of experience is worth more as a skill file than it ever was as a resume line. Write down your approach and your agent inherits it. Moment 5. Everyone in that room has watched an agent nail 10 steps and faceplant at step 30. Diana asks the man who runs agents for weeks, "What's actually breaking?" His diagnosis comes with 2 fixes you can ship this week.
But as you observe today, they sometimes stop working after 10 interactions with tools and so on. And sometimes that's because the model is trying to do something it doesn't have a lot of experience doing. So it's been trained on a whole set of things. And as soon as you get a little bit off the distribution of things it knows how to do, then like most machine learning models, it will, its performance will suddenly start to degrade. And the farther you get off the comfort zone of what it knows how to do, the more likely it is to not work as well. So there's a bunch of things you can do. So one is, give the model skills and hints that kind of tend to keep it in the sort of more brightly lit path of things it does know how to do. I think, having multi-agent systems where you have multiple agents trying different approaches and you can evaluate, you have maybe another model or another agent that's evaluating which ones of those seem promising is another way to kind of, in some sense, search the space of possible solutions and stick to the ones that seem most promising and discard the ones that didn't seem to work or maybe that went off the rails or whatever. And that's a very, very useful general technique is, inference time compute to perform search over plausible ways of solving the problem that can get much, much higher performance or much more reliability in long-running agent flows.
2 fixes. First, agents fail when they wander off the distribution of what they know. So you write skills that keep them on the brightly lit path. That's not documentation. That's guardrails for a probability distribution. Second, don't send one agent. Send several down different approaches and put an evaluator model at the end to keep what's promising and kill what went off the rails. Search, not hope. Every serious coding harness added a multi-agent mode this year. Now you know the reason. Moment 6. The one Y Combinator named the whole talk after. Diana asks where a 2 or 3-person team can still win, while Google compounds on everything general. His answer is a filter you can run on your startup idea in 60 seconds.
Second, I think you want to look at what the current more general models can do in that problem domain, right? You can test them with like, are they able to do this thing very well? And if they're completely failing, that's probably a good sign. If they're kind of able to do some of it, but not very well, that's maybe not a great sign because that's probably a sign that the capability is starting to be present in those models. And with more training data or larger scale models or whatever, it's likely to get better. So, look for something where the model succeeds 0% or 1% of the time, not 20%.
Read the rule back because it's backwards from instinct. If the frontier model already succeeds 20% of the time, walk away. That capability is emerging. And the next release eats your startup. If it fails completely, that's your opening. And he names the two durable openings: products that see personal data the general models never will, and AlphaFold shaped models, small, affordable niche models that crush one domain, like protein folding did on its way to a Nobel Prize. Grade your idea tonight. Is the model at 1% or 20? Last moment. When agents write all the code, what's left for you? His answer? Taste, knowing what's worth asking for. And then Diana pulls out the story that proves even his taste got rejected.
Yeah, I mean, I think it's really having incredibly good taste in what you ask your agents to work on, right? That is the crux of, from my background, a research problem. A researcher can have all the tools and all the techniques, but often most of the battle is what problem are you going to spend your time on? And if you pick the problem well and you succeed in solving it, that's way better than if you, delightfully execute a research investigation into a rather boring problem. And so that high level wisdom of what to work on, I think, is incredibly important.
So, how good is Jeff Dean's taste? In 2014, he co wrote a paper with Jeffrey Hinton on distillation, using a big model to teach a small one. The reviewers threw it out.
Yeah.
And the thing is, this paper got rejected at NeurIPS.
Yeah. I mean, I think I don't fault the program committee because, a lot of times a paper gets 3 reviews and one of the reviewers will look at it. And in this case, they said, oh, it's unlikely to have significant impact.
Unlikely to have significant impact.
But, I think, when we wrote the paper, we actually saw this was a super important problem because we knew making cheaper, highly capable models from larger scale models was something we desperately wanted to do because we wanted to serve models to more and more people in many different domains like speech or vision. But sometimes the reviewer maybe didn't have that experience because maybe they're not thinking about large scale AI services and are thinking about is this a fundamental advance? So it gets rejected every so often. That's fine. We put it on archive. People read it. People use it. It's all good. And we do use it in making our Flash models, for example, from our larger scale Pro model. That's partly why our Flash models, for example, in Gemini, are so capable relative to their size and speed.
They're some of the best in the benchmark for the model size class,
Yeah.
which is impressive. And I think part of the lesson is that even if you get rejected, keep going.
Yeah, that's the lesson I would distill from that.
That rejected paper is now one of the most cited in machine learning history. And distillation is how every fast, cheap model you use today was made. The gatekeepers called it insignificant. He put it on archive and kept going. And his final filter for what deserves years of your life is the same one. If the best possible outcome happens, is the world a lot better or just kind of cool? If the answer is kind of cool, pick a different problem. 7 moments. Agents already run for days or weeks. The ceiling is your verification, not the model. One napkin calculation became the TPU. Do the math on your bottleneck tonight. Compute is cheap. Moving data is 1,000 times the cost. Energy explains everything from batching to your streaming speed. His performance skill is public. Hand your expertise to the model as a skill. Agents die off distribution. Light the path with skills and search with evaluators. Build where models succeed 1% of the time, never 20. And when they reject the thing you know matters, publish it anyway and keep going. We condensed this into the Napkin Brief, a free PDF with every quote timestamped to the full talk, The 1% rule as a checklist you can grade your idea against, the Napkin Math worksheet, and the direct link to Jeff Dean's Performance Hints document with the steps to turn it into a skill. Comment the word napkin on this video and our assistant sends it over. Or grab it at hyperautomationlabs.co/free/napkin. Real talk. 90% of you watching haven't subscribed. On Facebook, subscribe is the supporter button. That is what keeps the lights on here. On YouTube, it's free and it tells the algorithm to send you more. Subscribe to support us. If you're starting out with AI coding tools, the beginner guides are linked below. The complete Claude code guide, the codex guide, the co-work sales guide, and the architect prep kit. Step by step from zero. We're on YouTube, Facebook, and Instagram as Hyperautomation Labs. Same name everywhere. And tonight, before you write one more prompt, do the napkin math on the problem you're solving. If the model's already at 20%, aim bigger. See you in the next one.